gradient descent simply means you follow the gradient until you're at the minimum of your loss function. And just as a cool example, which kind of got me quite excited that this is possible. So imagine you have the following problem. This is the water height field simulator. So just like water bin with, to see how the water height evolves. And the target is you want to flow the water into something that looks like the Tai Chi symbol. It's the Tai Chi symbol because that's the programming language that the people invented to do this. Name of the programming language. And the target is to find the initial velocity, the initial height field that after a certain amount of time leads to this. You can imagine that this is a hard problem to solve if you just have the simulator at hand, because this here has like thousands of degrees of freedom, and it's super nonlinear. Actually not sure if it's nonlinear. I have to look at the equations. But okay, it's a hard problem, and there are other examples for this. So what you can do here in this case is you can write just down a loss function. If this here is the simulator where you start with the initial velocity field and initial height field, and say, okay, minus my result. And if the simulator is auto-differentiable, you can just auto-grad through the thing and optimize the loss function. And what you will find is the initial height field that leads to this. And it's basically, once this code here is auto-differentiable, this like optimization step is like a 3-liner or whatever. So you can use techniques that also used for training neural nets. And you see it kind of, it works, right? I mean, this is where you start and then everything flows around. And at some point it ends up here. And there are quite a few examples for this. And similar techniques are already used like in biology and whatnot, but not very much in our field directly. And, what we started doing with this up to now is to throw it at strong lensing, which is much easier. You don't have a dynamical system that you have to solve. The only thing that we really did was to take the physics of strong lensing and put it in a auto-differentiable programming language. And this, yes, you all know about this. So the idea is simply you have a distant galaxy. We look at galaxy-galaxy lensing. In our case, we have a distant galaxy. We don't know how it looks like. We have like a galaxy along the line of sight, which acts as a lens. And then we get a lensed image, which here, this is a mock image. We actually didn't model the galaxy in the center, so that's why it still looks easy. But the trick is then to reconstruct from this kind of image, which is kind of ELT mock data-ish, this original source, as well as information about what's going on here in terms of dark matter distribution. And then hopefully learn something about, of course, the dark matter halo of the lens, but also the substructure of dark matter. And the substructure is very informative about particle nature of dark matter. That's why you're interested in this. So that's a very hard problem. There are several groups working on this, and we started to do this as well. And our philosophy was, as I said, to put the entire thing in the auto-differentiable setup with the goal of better modeling sources and figuring out how to do better source regularization and just get results faster, but then also faster inference of substructure properties and so on. And it's a really hard property because, I mean, before I was working on gamma rays, right? And I didn't really appreciate that lensing is complicated, but it's a mess because you have one image and you want to get back two. That's an image, and in principle this here is the column density of dark matter, which is another image. So you try to get two things from one, and there are lots of degeneracies involved. But still we got interested in this. And this here is the kind of setup. I mean, it's just showing like the logical flow. There is a lens model, which in our case is still simple, just analytic model in most cases. Then there's a source model, which we started playing with. And then there is the lensing physics, which we all coded up in PyTorch, so the machine learning language. And this then feeds into a likelihood function, so just a Gaussian likelihood, which compares with observations. And yeah, these are the libraries that we use. This is from Facebook, this is from Uber, and this here is, I don't know what. This is all from big companies. Good, so one thing that we tried to do, so one challenge here is to regularize the source, right? So if you would allow a source, if you would just take a pixelated source and allow arbitrary freedom, you usually get very, very rubbish results because you get just unphysical results. So you have to regularize how the source could look by basically assuming it's smooth at certain scales in order to get any meaningful results. And that's a challenge because you have to define like the hyperparameters that describe how smooth your source should be. And one interesting thing that we tried was to see if we could replace the source model, so the pixelated source model, by a neural net that is trained on real galaxy images and acts like as a parametric model for sources. So what we did is, yeah, there's earlier work on training neural nets to generate galaxies, for instance, Ravan Baksh from 2016. We did something similar on the galaxy end, but then put it in a strong lensing pipeline. So what we did is we took galaxies from the grade 3 catalog, which is used for training weak lensing pipelines. There are lots of galaxy images at redshift of, if I remember correctly, 1 and below. And then we trained a variational autoencoder that takes these images, compresses these images into latent space, so these were 64 dimensions in our case, and then we decoded it back to get something that looks like the original galaxy that we put in. And one can train these autoencoders just to generate galaxies. And you see, if you in the trained autoencoder plug in a galaxy, we get something out that looks like the input image, roughly speaking, with some additional smoothing. So this works reasonably well. But what's interesting is, here we have like, this was 64 by 64 pixels, I think. So large number of parameters. Here we just had 64 parameters, so 64 times less parameters. So it's an enormous reduction in complexity in terms of number of parameters that you have in the problem. And that's something we then exploited. But before I go to this, first I want to show you how the galaxies look like. So if you plug in a galaxy, project it onto a point in latent space, and then get back a galaxy, then you get something typically that looks like galaxies. But if you would just randomly take a point in latent space and generate a galaxy from this, usually you just get something blobby. So that's an example. That's not our best model that we had, but I just want to give you an idea. So what this here shows is the following. This is a true image from the grade 3 catalog of some weird galaxy or multiple galaxies. And what I do here is to take basically this image and generate data which has tiny noise here and tons of noise here. And then I want to find a good fit of our variational autoencoder to that object. And what you expect is like, okay, where you measure this feature, it's picked up, and this here is just kind of a random extrapolation of how the galaxy looks like. It doesn't have to look like a galaxy. And what? Sorry? No, not at this stage, because so on the, you mean in terms of the PSF that underlies the grade 3 catalog, or at a later stage when comparing? Yeah. So we did up to now we didn't include any PSFs at any point, which however is not the technical.
If we use the observational catalogs,
yeah,
then you need, right?
That's true. No, we didn't include that, but in general, what this should lead to is sharper images in some sense. The problem is anyway that with the variational autoencoder we get somewhat too smooth images. So even if we don't try to correct for any PSF effects. So I think at this stage for that particular application is not the main problem. What I wanted to show you is if this works, right? So this here is kind of a video. So if you see here basically how the variational autoencoder runs through latent space and tries to find a good fit to this data as I reduce the noise level over and over. And you see that it picks up like the structure that becomes visible, and in the rest it just randomly runs around. And at some point it gets like zipped into the real thing. It's just nice to look at it because you get an intuition for what kind of typical structure this variational autoencoder can generate. Good, so we then used this for strong lensing. Okay. For strong lensing, and you see it works. So we can plug in the variational autoencoder's source. We generate mock data that is independently generated. We fit the entire thing with Hamiltonian Monte Carlo. We can reconstruct the source, and we can reconstruct the image, and we get a reasonable reconstruction of the lensing parameters. And this is all reasonably fast since we use Hamiltonian Monte Carlo, so you don't sample for ages. You just get reasonably quickly, like 300 reasonably uncorrelated points, and then can explode posteriors. What we however found, not surprisingly, is as soon as the images get a very high quality, as noise goes down, we also get biases in the result. And the reason is simply that with 64 dimensions, obviously you cannot model an arbitrarily good measured, like high resolution image. So that's kind of the limitation of this. What we started then is to replace the entire thing with Gaussian. Okay, but I should say what this method shows is that you can actually combine deep neural networks as part of your physics model or your simulating model. And you certainly, so we run into problems, for instance, for the lens, for the source, but for the lens, which is much harder to measure, it might be actually a quite good thing to have a variation autoencoder trained in n-body simulations and use this in the fit. So the overfitting or underfitting problems wouldn't be so much of an issue, presumably. Good, what we did is then to replace the source with the Gaussian process instead with some custom implementation. I don't really have time to go through this. I skipped this, but you can see that we actually get reasonably good reconstruction of sources in that case. So this is based on ELT mock data, and this is just a very fast reconstruction of the source data. It looks reasonably good. So there we basically get zero residuals, even if you have very, very high, very low noise data. How many minutes do I still have? 10. Okay, good. Then I have enough time. So what I really am interested in, what kept me busy like half the year, last half year probably, is substructures. So the reason why we got started is we want to see small substructures in the dark matter halo. And they would show up basically, so this kind of image you get from the main lens, right? This generates the image. But then small subhalos that might, we only consider subhalos of the main lens, small subhalos that lie here along the